joining my talk. Today I'm going to talk about distributed transactions across microservices, why we need some pattern, why we need some definitions about distributed transactions across microservices. The contents of this talk will be specifically why we need them, how the Saga pattern helps mitigate this issue, what is exactly a Saga pattern, what are the implementation models of the Saga pattern, and how we can implement Saga pattern in real-world applications. Firstly, please let me talk shortly about myself. My name is Arif. I'm lead engineer at Valtech. Almost my entire career I have been working with e-commerce applications, starting from smaller monolithic applications to mid-size applications. Also have quite a lot of experience migrating or replatforming monolithic applications to Mac architecture. As you can see on the slide, I'm a Mac enthusiast. My first question would be, does everyone in this room knows what Mac is? Okay, besides the acronym that was already told, it stands for Microservices, API First, Cloud, and Headless. It's an alliance that helps and supports members to use this architecture. So yeah, in this talk we are going to be focused on the first letter of this acronym, which is the M, a lot of microservices. So let's dive deep into the issue that we are going to talk today, and that is maintaining consistency in different microservices. To understand this issue, we first need to go back in time where everything used to be simpler. So in the monolithic applications, in monolithic world, we have one huge application which consists of a UI, business logic, and data access. Most of the time, it also has one huge database, and it looks something like this. So we have UI, business logic, and data access layer, accessing usually one huge SQL database. Why everything was, I mentioned that everything was simpler, especially in maintaining consistency across our application. It's right because of this reason. We have one big database which we can use transactions in different ways. In Java, we can use transactions in all the languages that support transactions, which in translation, it will translate to the database transactions or query transactions. I mentioned that I have, during my entire career, I have been working with e-commerce application or retail customers projects. That's why during this talk, I'm going to take quite a lot of examples on how we can utilize distributed transaction or how we can utilize Saga in e-commerce application. But first things first, let's start with an example of e-commerce application in monolithic world. So we have a shop which we need to create an order. Then after the order is created, we need to update the inventory. After the inventory is updated in background, we need to process the payment. After the payment is processed, we need to notify the customer by sending them an email, right? This is the happy path, and there are also customers that will come to you and say, but I am B2B shop, and you need to check before making a transaction, you need to check whether the customer credit limit allows him to make this particular order. In a monolithic application, that is quite simple. Let me put it that way, because we have one big giant application where we can start a transaction, we can create an order, we have a function created with the order, we can update the inventory, we can process the payment, notify the customer, check in the table, customer table, whether that customer has a limit. If it has a limit, query the orders table, check, do some calculations, etc. But everything in monolithic world, or in one application, when there is one database, is ACID transactions, right? So all properties of ACID transactions are passed, and we are happy with it. But why we are choosing to move away from this happy path, why we are choosing to go away from this simple stuff, is because monolithic applications are pretty hard to scale. So if you want to scale one part of the application, that's impossible. You need whether need to scale the whole application or not. That's the one biggest downside of these monolithic applications. And also, there is if the company grows, if the company is successful, this code base grows quite a lot. Of course, if the company is not successful, it won't grow, but it will die eventually one day. But if it grows consistently, that means that maintaining that code base gets harder and harder. That's why we come to the world of microservices. Microservices, I would say, is both architectural and organizational approach. In architectural, it's easy to understand, because in the previous slide that I showed, we have orders, we have customers in one big application. In microservices, we would have a service for orders, a service for customers, a service for payments, etc. But it's important to keep in mind that it's not enough if you just have this approach, like architectural approach. What you need to do in order to be successful in your implementation of microservices or replatforming from monolithic to microservices is that you need to understand that it's also an organization approach. What does it mean? If until today your organization worked with monolithic and your whole team knew everything about that application, when starting of replatforming, or when on the process of replatforming, you need to divide the team in smaller teams. So what does it mean? The teams that will be divided, the smaller teams, will be self-contained teams, and they need to understand what they are doing in that particular service or services that they are working on. This has a lot of benefits, of course, because when you're training a newcomer to the company, you don't have to explain them everything about the huge application that powers your system. You just need to, firstly, you need to onboard him on the part that he will, or she will be working on. This is just one of the benefits. Other benefits are, of course, that you can scale. You can scale just the part of the application that needs to be scaling, etc. So, how would a high-level architecture of microservices look like? So we have, of course, we have a lot of microservices, which sits in the middle of this diagram, and also we can have micro frontends. Here I have included as much as possible of different technologies. I hope this is never realistic in a real project, but I have seen cases where the CTO or a manager comes and says, "Hey, I have seen a cool YouTube video last night about Go or Rust. We need to implement a service about that." So it's fine, we can do it. In this particular example, we have orders, which is using Vue. Then we have a service that is powering that front end, which is using Node.js. Then we have a data source per service, which is very important to mention. By default, by definition of microservices, you need to have a data source or database per service. Otherwise, you are breaking the rules. my account, in this case, uses Angular, and it's powered by a Go application backend, and data source is Postgres, and the catalog is powered by React. It's using Python, and in this case, it doesn't have own database. That's why I mentioned it data source. It is powered by a third-party API, which is perfectly fine. Okay, if we translate everything that was in previous slides about monolithic, if we translate that to a microservices about in e-commerce world, it would look like something like this. This is a REST application which has an API gateway in the middle, and we have orders microservice, inventory microservice, payment microservice, customers microservice, and notify microservice. Each of those services powered by their own data source, which is perfectly fine. So we are having database per service or data source per service, which doesn't allow us to have asset transactions. Just because we cannot query one single database and start and end a transaction in that single database, it means that we cannot have asset transactions. What would we do in this case? And how Saga pattern helps mitigate this issue? As I mentioned the earlier case, where we have a customer that is putting an order, imagine in this microservice world scenario, order is created, payment is done, inventory is reduced for that particular product or products, and then it comes, the service is being called to check whether the customer that is placing the order has enough credits to place the order. If something fails here, the customer will have reduced amount of money in his cart. The inventory service will have wrong inventory for that particular product. The order will sit stale in our database, order database, and everything, our service, basically our system, will have inconsistent data. How we can solve this is by implementing the Saga pattern. Saga pattern, by definition, is a microservice architecture pattern for managing distributed transaction. It organizes a series of local transactions where each service executes its part and triggers the next step. If any transaction fails, compensating actions are executed to undo the previous operations. Which means that if, in our case, if the customer service fails, we need to go back and undo every operation that we have done until that particular moment. In this case, we have order service, inventory service, payment service, and notify service. And if you can see, if something bad happens, which is this red dot here, if something bad happens in notify service, for example, notify customer that something bad has happened, and then refund the payment, restock the inventory, and revert the order. If something bad happens in inventory service, we need to call restock inventory, and then restock inventory will call the revert order. How we can implement this? What are the implementation models? There are two implementation models. The first one is choreography, which by definition is each service decides the next step in the transaction. If we can see in the this design here, we have the service calling inventory service. Most of the cases, and I hope it's always that case, this is done by event-driven architecture in background. So order service will send or will push an event to an event bus, and that automatically will trigger inventory service, and inventory service will push a message queue to a queue that we choose, that will trigger payment service, etc. One of the pros of this approach is that easy to understand. So it's straightforward. We have order service which needs to push a message to a message bus, which will trigger another service, and it goes like this. But what happens if we need to put the customer service in this design here? What happens if the manager comes to us again and says, from tomorrow we have that Rust service ready and we need to put it between inventory service and payment service? What will happen? We need to go to the inventory service, change the code of that service to push messages instead of triggering the payment service. It now needs to trigger customer service, go in the customer service, add a piece of code that will trigger a message to trigger payment service. So it's hard to create a new service and hard to monitor and debug what goes wrong. But in other way, when something goes wrong, the compensation path is all the way around. So if notify service in the previous example that I showed, if something bad happens in notify service, it will trigger payment service and it will go back to the first service called, which is the order service. What if compensation service fails? Then we will have inconsistent data again, because even if we have retry mechanism, we'll retry once, twice, third time, and we cannot retry for forever. So in this case, we can end up again with invalid state in our system. That leads us to orchestration, which is, in my opinion, is the way to go when implementing the Saga pattern. And to be honest, it's most commonly used model. In orchestration, as it can be seen in the diagram here, we have one extra service, which we call the orchestrator. What does it do? It knows everything about the other service sitting in background. So we can orchestrate every single step in our Saga pattern. Scaling, what are the cons of this approach? Scaling is limited by orchestration capacity, but we will see a little bit later in the slides that this is not very true in nowadays, especially if you are implementing Saga patterns in cloud native applications. But what are the pros? It's easier to code, right? Because we are coding order service. We don't need to take into consideration that order service will actually need to call inventory service. Easier to debug and monitor. If something bad goes in order service, we will be surely that order service fails and not some call to another inventory service or to another, for example, to while pushing the notification or the message to a queue. So order fulfillment orchestrator, in this case, we'll call order service, inventory service, payment service, and notify service in the happy path. But in the compensation path, it will go, depends where it fails. If it fails in notify service, it will have to call every and each compensation of those services. What are the implementation options? As I mentioned earlier, while implementing this Saga pattern in a world of cloud, the limitation of orchestration gets, it's not, for sure, we cannot say that we can scale how much we want, but hitting those limits, it's quite hard. One of the implementation options is Apache iFlow, which is a management workflow SaaS provided by Apache. We have Step Functions or Azure Logic Apps, which are services provided by, in this case, by AWS, by Azure, but GCP has them as well. We can utilize these services to implement easily the Saga pattern. In this slide, I've shown two real-world scenarios of AWS Step Functions. So in the first step, we don't have have any services failing, so everything is green. In the second, in the right side of this slide, we can see that process payment failed, and this means that we need to trigger payment refund, roll back the inventory, and cancel the order. In both cases, we need to notify the user that something good or something bad happened. I have set up a working example, which we don't have the time to go through now, but you can check, you can scan this QR code and you can check in GitHub. It's basically a small application, a blueprint that consists of Node.js code. It deploys this code into AWS using SAM, infrastructure as code provided by AWS. I think it has 3 or 4 services, which will eventually, if you provide the right environment keys, the right keys in the right way, you end up with something like this in AWS. Thank you. Thanks a lot.